Hello, in this lecture we'll find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. We know that line segment AC equals to 5 units in its length. This is line segment CB that is equals to 1 unit in its length. Our mission is to find out the area of this green semicircle. Okay, so first of all, we'll join points P and B together by a straight line. And joining points P and B together, we actually created here peritriangle APB. So I'll copy the white semicircle in a new page and we'll implement the rule 7 on the white semicircle. Actually, this is the white semicircle that I copied from the original drawing. By joining points P and B together by a straight line, we created peritriangle APB. And we know that AB is the diameter of this semicircle. So I'll write it down. AB is the diameter of this semicircle, or AB is the diameter of the white semicircle. So AB is the diameter of the white semicircle, and we have peritriangle APB that is subtended on AB, that is the diameter of the white semicircle. So here we can implement rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtended on the diameter of the circle, then it is equal to 90 degrees in its size. So we have here a circle, and AB is the diameter of the circle, and we have a peritriangle ACB that is subtended on AB, that is the diameter of the circle. Therefore, peritriangle ACB must be equal to 90 degrees in its size because of the fact that is subtended on AB, that is the diameter of this circle. So whenever you have peritriangle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peritriangle APB that is subtended on AB, that is the diameter of this semicircle, and therefore according to rule 7, peritriangle APB must be equal to 90 degrees in its size. So peritriangle APB equals to 90 degrees in its size according to rule 7. In the next step, we will join points P and C together by straight line. Here by joining points P and C, we can do the angle APC. So I copied the green semicircle in a new page and we implement rule 7 on this green semicircle. So actually, this is the green semicircle that I copied from the original drawing. Actually, by joining points P and C together by a straight line, we created the peripheral angle ACP. This is peripheral angle ACP, and AP is the diameter of the green semicircle. So I'll write it down. AP is the diameter of this green semicircle. AP is the diameter of this green semicircle, and we have peripheral angle ACP that is subtended on AP, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle ACP must be equal to 90 degrees in its size. So this angle ACP equals to 90 degrees in its size according to rule 7. You can see in the original drawing, this angle A is a common angle. It belongs to the green right triangle APC, and angle A also belongs to the right triangle APB. Therefore, angle A is a common angle that belongs to both triangles. Okay, so we define angle A, this common angle, angle A is alpha. So in the right green triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing third angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, this is the common angle, angle A, that we define this alpha. You can see here, it belongs to the white triangle APB and to the green triangle APC. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing third angle here must be equal to 90 degrees minus alpha. So in the next step, I'll copy this right triangle APB with this right angle APC in your page, and we'll prove that those two right angles are similar to each other according to angle similarity rule. So here, those are the two right angles that I copied from the original drawing. In the next step, we prove that those two right angles are similar to each other according to angle similarity rule. So this is the right triangle APB, and we'll prove that it is similar to this right green triangle APC. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle APB in the right triangle APB, and it is equal to this angle, that is actually angle ACP in the green triangle APC. Repeat again. Angle APB in the right triangle equals to angle ACP in the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. Those two angles, angle alpha, it is actually a common angle that belongs to both triangles. So angle alpha equals to itself as a common angle that belongs to both triangles. So if we write to angle alpha as it is belongs to the right triangle, it will be defined as angle PAB, and it equals to itself. So if we write to angle alpha as it is belongs to the green triangle, it will be defined as angle PAC. So I repeat it again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Okay. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ABP, the right angle APB, and this is equals to this angle. It is actually angle APC in the green right angle APC. Repeat again, angle ABP in the right angle APB equals to angle APC in the green right angle APC. They are both equals to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the three angles in this right triangle APC are correspondingly equal to all the three angles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. So the right green triangle APC is similar. This is the sign of similar to the right triangle APB according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. Here, before we continue, we know that AC equals to 5 units in its length, so I write it down, AC equals to 5 units in its length, and this is side AB that in total equals to 5 plus 1, that is 6. So side AB equals to 6 units in its length. So because of the fact that those two right triangles are similar to each other, the following relationship exists between their sides. Side AB in the right triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. And again, we conclude that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. AB equals to 6 over AP. AP is the missing side, so we leave it as it is. And it is equals to AP over AC. AC is 5. So in total, we actually found out that six over AP equals to AP over 5. Here we cross multiply this equation and you get that 6 times 5 is 30. So 30 equals to AP times AP, that is AP squared. Here we take a root out of this equation and finally we get that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AB. This is equals to square root of 30 units in its length. AP is the diameter of this green semicircle. Therefore, the diameter over 2 is the radius of this green semicircle. So we define the radius as R of the green semicircle. The radius R must be equal to the diameter AP over 2. AP is equal to 30. Therefore, AP over 2 is equal to 30 over 2. In conclusion, we shall find out that the radius R of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. So the area of the green semicircle equals to the area of the circle over 2. And the area of the circle is of course pi r squared, and pi r squared over 2 is the area of the green semicircle. So the area of the green semicircle equals to pi times r squared. R is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. So in total, the area of the green semicircle equals to the value of this expression. We open the brackets here and we get that the area of the green semicircle in total equals to pi times square root of 30 square is 30 over 2 square is 4. So it is over 4 divided by 2. So it is pi, and 30 over 4 over 2 is 30 over 4 times 2. Here 30 over 2 is 15. So in total this expression will be equal to 15 pi over 4 square units. 15 over 4 is 3.75. So in total this expression equals to 3.75 pi square units. So actually found out that the area of this green semicircle equals to either 3.75 pi square units. In terms of numbers, the area of this green semicircle equals to 11.78 square units. Repeat again, we actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. Okay. In the second method, we'll join points P and B together by a straight line. In the next step, I'll copy the white semicircle in the new page, and again we will implement rule 7 on this white triangle, this white semicircle, exactly as we did in the first method. Actually, this is the white semicircle that I copied from the original drawing. We know that AB is the diameter of this semicircle, so I'll write it down. AB is the diameter of the white semicircle, this semicircle. Actually, by joining points P and B together by a straight line, we created a peripheral angle APB. This peripheral angle APB is subtended on AB. Again, this peripheral angle APB is subtended on AB, that is the diameter of the semicircle. And according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle APB must be equal to 90 degrees. According to rule 7. AP is the diameter of the green semicircle. Again, AP, this is 9/7 AP. It is defined as the diameter of this semicircle. Again, semicircle. We define the center of this green semicircle. This point is point O. Therefore, PO is the radius of this green semicircle. We define the radius as R. So PO equals to R according to our definition. Okay, PO equals to R. So I will copy the green semicircle with 9/7 PB, and we've already found out that peripheral angle APB equals to 90 degrees in its size. So this is peripheral angle APB that is equal to 90 degrees in its size. So I'll copy the green semicircle in the new page with this 9/7 BP. So actually, this is the green semicircle that I got from the original drawing. We have a 9/7 BP that creates 90 degrees with the radius PO. Again, 9/7 BP creates 90 degrees with the radius PO. That is to say, BP is perpendicular to the radius PO. Again, BP is perpendicular to the radius PO because this angle equals to 90 degrees in its size. Therefore, we can implement here rule 1 Repeat quickly on rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have the radius OM that is drawn to point M, that is the point of tendency of line segment AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then AB will be perpendicular to MO, to the radius MO. And because of the fact that AB is perpendicular to MO, it means that AB is the tangent to this circle at point M. Again, because of the fact that AB is perpendicular to the radius MO, AB is the tangent to this circle at point M. So I can actually implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP is perpendicular to the radius PO, and according to rule 1, whenever you have a line segment that is perpendicular to the radius PO, it is defined as a tangent. Therefore, BP is tangent to this semicircle at point P. Again, because of the fact that line segment BP is perpendicular to the radius PO, it means that line segment BP must be a tangent to this semicircle, green semicircle at point P. So I write it down. I should find out that this line segment BP is tangent to this green semicircle at point P. Okay. So here we have BP is tangent to the radius PO, so I write it down. BP is tangent to the radius PO of this green semicircle, and from the same external point, point B, we have also, when we extend when we draw from point B, also straight line towards the green semicircle, it cuts the circle at 2 points, C and A. So from the common external point, point B, we have chord CA. CA is chord of the green semicircle, and we have also from the same external point, point B, we have also tangent BP, that is tangent to this semicircle at point P. So here we can implement rule 10. I repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord in the circle, here we have chord AB, and PT is tangent to the circle, we have here tangent PT, that is tangent to this circle at this point, point T. Point T is the point of tendency of tangent PT with this circle. So in this drawing, the following equation will be true, that PT squared, it is the square of the tangent PT, equals to PA times PB. Again, PT squared equals to PA times PB. So we can actually implement rule 10 in our drawing, because in our drawing we have tangent BP, that is tangent to this semicircle at point P, and from point B I'll copy the straight line BA in the new drawing. Again, from the common external point, point B, we have tangent BP, that is tangent to this semicircle at this point P, and we also have is this straight line that cuts this semicircle at 2 points, point A and this is point C. So in conclusion, we actually have here from the common extent point B we have chord CA, and from the same common extent point B we have also tangent BP that is tangent to this circle at point to this green semicircle at point P. That is to say, all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, we get that BP squared equals to BC times BA. Again, BP squared equals to BC times BA. So I write it down. According to rule 10, in this drawing, we get that BP squared, that is the square of tangent BP, must be equal to BC times BA. This is according to rule 10. This equation is the implementation of rule 10 in our drawing. BP is the missing tangent, so we'll leave it as it is. So it is BP squared equals to BC. BC is 1. Here you can see that BC is 1, so we substitute BC by 1, and AB in total equals to 5 plus 1, that is 6. Again, AB in total equals to 6. So BC is 1, so we substitute BC by 1, and BA or AB in total equals to 6. So in conclusion, actually found out that BP squared equals to 1 times 6, that is 6. BP squared equals to 6. We take a root out of this equation, and finally we get that the missing tangent BP is equals to the square root of 6 units in its length. So here BP equals to the square root of 6 units in its length. In the next step, I'll copy the right triangle ABP in a new page, and we will implement the Pythagoras theorem on this right triangle ABP in order to find out the missing side AP, because we know that this side BP equals to the square root of 6 units in its length. Here BP equals to the square root of 6 units, and the hypotenuse AB equals to 6 in total. Here the hypotenuse AB equals to 6 units in total. The only missing side is side PA. So I copy the right triangle APB in a new page, and we will implement the Pythagoras theorem on this right triangle APB in order to find out the missing side AP. So actually, this is the right triangle BPA that is covered from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle BPA is BP, is AB, therefore the square of the hypotenuse is AB squared, and it must be equal to BP squared plus PA squared. Okay. So here we subtract BP squared from this equation, And we get that the missing side AP square equals to AB square minus BP square. So the missing side AP square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, minus BP square. BP is square root of 6, therefore BP square is square root of 6 squared, that is 6. So in total, AP square equals to 36 minus 6, that is 30. AP square equals to 30. Here we take a root out of this equation, and finally we get that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP. This is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle. If the diameter AP equals to the square root of 30 units in its length, it means that the radius must be equal to half of it. The radius must be equal to AP over 2. So we define the radius. We already defined the radius of this green semicircle as R. Therefore, the radius R must be equal to the diameter AP over 2. And again, the radius R of this green semicircle equals to the diameter AP over 2. We just right now found out that AP equals to the square root of 30. Therefore, R equals to AP to the square root of 30 over 2. So, in conclusion, we found out that the radius of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle will be equal to the area of the circle, that is pi r squared, divided by 2. So it is pi r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. So here we'll open the brackets and we get that the area of the green semicircle in total equals to pi, and square root of 30 square is 30 over 2 square is 4 divided by 2. So the area of the green semicircle equals to the value of this expression. The value of this expression is pi, and 30 over 4 over 2 is 30 over 4 times 2. So here we have 30 over 2 is 15. Therefore, in total, this expression will be equal to 15 pi over 4 square units. 15 over 4 is 3.75. So in total, this expression equals to 3.75 pi square units. Or in terms of numbers, it is equals to 11.78 square units. So if you find out, according to the second method also, that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. So in the next step, I will summarize the lecture. We start with the first method, of course. So in this lecture we found out the area of this green semicircle using two different methods. So we start with the first method. In the drawing we have two semicircles, the green semicircle and the white semicircle. In addition, I know that this is line segment AC that is equals to 5 units in its length. This is line segment CB that is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first step, we join points P and B together by a straight line. And then I copied the white semicircle in the new page and implemented rule 7 on the white semicircle. This is the white semicircle that I copied from the original drawing. AB is of course the diameter of this semicircle. By joining points P and B together by a straight line, we created a peripheral angle APB. This is peripheral angle APB, and peripheral angle APB is subtended on AB, that is the diameter of this white semicircle. Therefore, we can implement rule 7. I repeat quickly rule 7. According to rule 7, if a peripheral angle is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So here we have a circle, and this is a line segment AB. This is the diameter of this circle. And we have here peripheral angle ACB. This is peripheral angle ACB that is subtended on AB, that is the diameter of this circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size, because it is subtended on AB, that is the diameter of this circle. We can actually implement rule 7 in our drawing. Why? Because in our drawing we have AB is the diameter of this white semicircle, and we have peripheral angle APB that is subtended on AB, that is the diameter of this semicircle, and therefore peripheral angle APB must be equal to 90 degrees in its size according to rule 7. So this is peripheral angle APB, and it must be equal to 90 degrees in its size according to rule 7. Likewise, we joined points P and C together by a straight line. Then I copied the green semicircle in the new page and implemented rule 7 on the green semicircle. This is the green semicircle that I copied from the original drawing. Again, AP is the diameter of this green semicircle. By joining points P and C together by straight line, we created peripheral angle PCA. This peripheral angle PCA is subtended on AP, that is the diameter of this green semicircle, and therefore, according to rule 7, peripheral angle PCA must be equal to 90 degrees in its size. Okay? So here we have line segment AP, line we have here two triangles, triangle APB, and we have also the green triangle, triangle APC. And angle A is a common angle that belongs to both triangles. So I copied those two right triangles in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So this is the green right triangle APB that I got from the original drawing, and this is the right green triangle APC that I also copied from the original drawing. Repeat again that angle A is the common angle that belongs to both triangles. You can see from the drawing. This is angle A that belongs to the green triangle APC, and then angle A also belongs to the right triangle APB. Therefore, angle A is the common angle that belongs to both triangles. So we define the common angle A as alpha. So this is angle A that we defined as alpha. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle A must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we defined the same angle A as alpha. So in the green right triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the third missing angle must be equal to 90 degrees minus alpha. So in the next step, we proved that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. That is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles in the right green triangle APC are correspondingly equal to all the three angles in the right triangle APB. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I repeat again, we actually found out that the green triangle APC is similar to the right triangle APB according to angle similarity rule. And from the fact that the green triangle APC is similar to the right triangle APB, we derive that the following relationship exists between their sides. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. I'll repeat again. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. AB equals to 6. AP is the missing side, so we leave it as it is. And AC equals to 5. And therefore, here you can see that AB equals to 6, AC equals to 5, and therefore this equation equals to 6, it means that 6 over AP equals to AP over 5. Here we just multiply this equation and finally found out that 6 times 5 equals to AP times AP, that is AP squared. 6 times 5 is 30, therefore 30 equals to AP squared. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. Actually, this is side AP, that is the diameter of this green semicircle, that is equals to square root of 30 units in its length. If the diameter AP equals to the square root of 30, it means that the radius must be equal to half of it. So the radius is AP over 2. Again, the radius R is AP over 2. AP is square root of 30, therefore AP over 2 is square root of 30 over 2. In conclusion, we found out that the radius of this green semicircle R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of the green semicircle must be equal to the area of the circle that is pi r square over 2. Because again, the area of the green semicircle must be equal to the area of the circle that is pi r square over 2. So the area of the green semicircle equals to pi r square over 2. So it is pi, r is square root of 30 over 2, therefore r square is square root of 30 over 2 squared divided by 2. We open the brackets here and found out actually that the area of the green semicircle equals to pi. Square root of 30 square is 30 over 2 square is 4 divided by 2. So in total, the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 equals to 30 over 4 times 2. So in total this expression equals to 30 pi over 4 times 2. 30 over 2 is 15. Here 30 over 2 is 15. So in total the value of this expression must be equal to 15 pi over 4. 15 pi over 4. 15 over 4 is 3.75, and therefore in total the value of this expression is 3.75 pi. So in conclusion, we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by third time. And then I copied the white semicircle in a new page, and again we implemented here rule 7 exactly as we did in the first method. So this is the white triangle, the white semicircle that I copied from the original drawing. We know that AB is the diameter of this semicircle. By joining points P and B together by third time, we created peripheral angle APB. This peripheral angle APB is subtended on AB, that is the diameter of this semicircle, and according to rule 7, whenever you have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. Therefore, peripheral angle APB, this peripheral angle APB must be equal to 90 degrees in its size according to rule 7. Okay? So here we have line segment BP creates 90 degrees with PA. But PA is the diameter of the green semicircle. PA is the diameter of the green semicircle. If PA is the diameter and O is the center of the semicircle, it means that PO must be the radius. PO is the radius of the green semicircle. So I copied point O from this original drawing to here. Here. I copied point O from the original drawing to the new drawing here. Point O is the center of this green semicircle. This is point O that I copied from the original drawing. So point O is the center of this green semicircle. Therefore, PO or OP must be the radius of this green semicircle. So we have BP, line segment BP creates 90 degrees with the radius PO. Why? Because we know that angle BPO equals to 90 degrees according to rule 7. And again, we already found out that angle APB equals to 90 degrees in its size. Therefore, line segment BP creates 90 degrees with the radius PO. And whenever you have a line segment that creates 90 degrees with the radius of the circle, you can implement rule 1. I repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have the radius OM that is drawn to point M, and here tangent AB is perpendicular to the radius MO. So because of the fact that line segment AB is perpendicular to the radius MO, line segment AB is defined as a tangent. So whenever you have a line segment that is perpendicular to the radius, it must be a tangent, according to this rule, rule 1. And here in our drawing, we have line segment BP that is perpendicular to the radius PO of this green semicircle. Therefore, line segment PB must be a tangent to this green semicircle. So PB is tangent to this green semicircle. So from the common extent point B, we have tangent BP to this green semicircle. Tangent BP is tangent to this green semicircle at point P. In addition, from the same common extent point B, we have this straight line that cuts this green semicircle at 2 points, C and A. In this way, we created chord CA. Okay, again, from the common extent point B, we have tangent BP that is tangent to this green semicircle at point B. In addition, we have also this straight line that cuts the semicircle at 2 points C and A. Therefore, in this way, we created chord CA. So actually, all the requirements of Rule 10 are satisfied. Therefore, we can implement Rule 10. Repeat quickly on Rule 10. According to Rule 10, Rule 10 is true in any circle. So in any circle, if AB is a chord, we can say that AB is a chord of this circle. And PT is tangent to the circle. Here PT is tangent to this circle at point P, at point T. So in this drawing, the following equation will be true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement Rule 10 in our drawing. In our drawing, from the common extent point B, we have tangent BP that is tangent to this green semicircle at point P. In addition, we have here this straight line that cuts the semicircle. In this way, we created chord CA. So again, all the requirements of Rule 10 are satisfied, and therefore we can implement here Rule 10. According to Rule 10, we get that BP square equals to BC times BA. Again, BP square equals to BC times BA. BP square equals to BC times BA. The tangent BP is the missing side, so we leave it as it is. So BP square equals to BC. BC is 1, so we substitute BC by 1 times AB. AB in total equals to 1 plus 5, that is 6. Again, AB equals to 6. AB equals to 6, so we substitute AB by 6. So in total, we actually found out that BP square equals to 1 times 6, that is 6. BP square equals to 6. We took out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in its length. So BP equals to the square root of 6 units in its length. In the next step, I copied the right triangle BAP in a new page and implemented the Pythagoras theorem on this right triangle BPA. We just right now found out that side BP equals to the square root of 6 units in its length. Side AB equals to 6. AP is the only missing side, so by implementing the Pythagoras theorem on this right triangle BPA, we will find out the missing side PA of this right triangle. So actually, this is right triangle BPA that are coming from the original drawing. Again, BA in total equals to 5 plus 1, that is 6. Here, BA equals to 6, and we found out that according to Rule 6, BP equals to the square root of 6 units. So according to the Pythagoras theorem, in this right triangle BPA, BA squared, that is the square of the hypotenuse, equals to PA squared plus BP squared. Again, AB squared equals to BP squared plus PA squared. Here we subtract BP squared from this equation, and finally found out that the missing side AP squared equals to AB squared minus BP squared. So the missing side AP squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36. Minus BP squared. BP is square root of 6, therefore BP squared is square root of 6 squared, that is 6. So in total, AP squared equals to 36 minus 6 is 30. AP squared equals to 30. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. AP equals to the square root of 30 units in its length. AP is the diameter of this green semicircle. if the diameter AP equals to the square root of 30 units, it means that the radius must be equal to half of it. So the radius must be equal to the square root of 30 over 2. Read again, the radius of this semicircle, that is R, must be equal to the diameter AP over 2. The diameter AP is square root of 30, therefore the radius R must be equal to the square root of 30 over 2. So the radius of this green semicircle R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of the green semicircle must be equal to the area of the circle that is pi r squared over 2. Again, the area of the green semicircle must be equal to the area of the circle that is pi r squared, and then we divide the area of the circle by 2 in order to find out the area of the green semicircle. So the area of the green semicircle in total equals to pi r squared over 2. So it is pi r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. We open the brackets here, we found out actually that the area of the green semicircle equals to pi times square root of 30 square is 30, and over 2 square, that is 4 divided by 2. So in total the area of the green semicircle equals to pi times 30 over 3 over 2. 30 over 3 over 2 equals to 30 over 3 times 2. So in total this expression equals to 30 pi over 2 times 4. Here 30 over 2 is 15, so in total this expression equals to 15 pi over 4 square units. 15 over 4 is 3.75, therefore in total this expression equals to 3.75 pi square units. So in conclusion, according to the second method, we actually found out the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. So in both methods, we arrived to the same result. Okay, thank you very much.